This is our week 6. Next week is reading week. Okay, so this is our week 6. And this is week 6. Really, Eugene? So our agenda for today, we are going to complete the example on sandwich material. Under eccentric, unsymmetrical, bending. Okay, we're going to complete the example. We finished grading term test 1. 25 students need to do correction out of 180. I will post the location of the whole of the correction later today. Most of the courses, when you take, what's the class average? Any idea? Hey? No, other courses beside this one. Any idea? Come on, give me a number. 75. Anyone else? That's about 75. Those over there, what was the class average? Any other courses that you take? Some are A minus, am I right? It's okay to tell me that. I know that, okay? Class average is C minus for 3A. And it's not bad. It used to be a F. Okay, so you guys are doing fine. Okay, don't kick yourself. Okay, you guys are doing fine. Okay, so it's not bad. There's hope, right? So let's go back to our problem over here. Right, let's go back to our problem over here. We are going to determine the maximum stresses in material 1 and in material 2. We have, and now this problem, as I said, is all about bending. Any topics about bending is here. You have eccentric loading. The eccentric loading is due to what? Let's quickly recap. The eccentric loading is due to the what? Axial loading. Am I right? Okay. And then you have bending moment occurring about 2 axes. You have bending moment about the y-axis. We also have bending moment about z-axis. Okay. So the formula we are going to use is shown down here. This is the formula that we're going to apply. Okay, so the first thing we did is we have calculate our normal stresses due to our axial loading. Right, we've done that. And then we are going to determine our stress X due to our bending moment. Okay, from then we find our IZZ. We also have identified what is our I. Did we do our IZZ? We only did our IZZ. Did we do our IYY? I think we did. We also have identified our IYY. The reference material we took over here is material 1, which is the brass. Then we did bending moment analysis. And this is really important over here. Okay. When the applied force is perpendicular to the centroid, the distance is to the point of failure. When the applied force is applied parallel to the centroid, the perpendicular distance is at the centroid. Okay. Now, I'm going to complete this problem first. Okay. Later today, in the second half of our class, we are going to do examples like this. Have you all seen questions like this before? Yes or no? Some of you, yes. Which course? Okay. No. This is worse than 3C. 3C is pretty straightforward. Okay. This is a bit mind-boggling. Okay. But the way I help you identify what's a bending moment is through visualization, not applying metrics. Are we clear? Okay, so that's what we're going to learn. Right, before we go over there, let's complete our problem. Okay, so doing the analysis, right? Let me bring us back to here. Okay, I'm gonna copy this diagram. I think this diagram is okay. So doing our analysis, we know there's a moment, there's a force. So this is the force, and the force is coming towards us. Okay, and then if I were to sketch the position of the neutral axis, sorry, centroid. If we were to sketch the position of the centroid, this position over here, and the position from the centroid from here to here, this distance, we know that distance is equal to, I'm looking for the, is 123.205. Okay, 123.205 millimeters. And then this is on the ZZ axis. And then we have another position of our centroid. This is about our YY axis. Okay. I'm going to also take the image from the cross-sectional view. Okay. So from the cross-sectional view, this is our, sorry, our longitudinal view. Okay. So this is our cross-section view. That's rotation about Z. And we know that if we are given a force down here, right, we have found the force down here. The force down there we found, I think that we calculate that force. Let me look at our values. I think we did. It is 8.66 times 10 to the power 3 Newton. Okay. And this force over here, right, is going to generate a moment about Z in this axis. Again, this rotation. So when you flip it around, this is our moment about Z, right? And also we realize that we have a axial load over here, which is equal to 5 times 10 to the power 3. Okay, but both of them will generate a moment in that direction. Then we know we have a moment in this way in Y. Because the force is coming towards us, it will generate that rotation. The purpose of doing this is to identify that this is under compression, this is under tensile. Over here, this is under compression, and this is under tensile. Okay, that is the purpose. So last week, we did calculate, okay, we did calculate the moment about Z. Okay, we did calculate the moment about Z. And the next thing that we're going to do now, right, we calculate the moment about Z, which is equal to what? Which is equal to 17.936 times 10 to the power 3. Okay. So now we are going to determine our moment about Y. Okay. We are aware there's a moment in the Y axis. So moment about Y will be equal to 5 times 10 to the power 3 multiplied by a perpendicular distance of 0.15 divided by 2. Okay. So when we write that, 5 power 3 times 0.15 divided by 2. Okay, so we have 375 Newton meter. This question is really, really important. You have seen the homework already, yes or no? Yes? Have you seen the homework for bending moment yet? Okay, I can pick any of those questions, change the direction of the forces, and split the beam up into a sandwich material. That is a very important hint. Are we clear? Okay, so this is very what? Important. Okay, take note. Daniel, happy birthday, dude. We're not going to sing a song, maybe later. So now, what we are going to do, okay, so the objective of this question is to determine the maximum bracket tensile or compression stresses. Sorry, not all. Here, N. Okay, maximum, determine the maximum normal tensile and compression stresses acting in the brass and steel. So we are aware that material 1 is brass. So let's handle for the brass material first. Okay, let's handle the brass materials. The general formula that we're going to apply is equal to stress X is equal to Px over, or I will not say Px over A, it depends on the axial stress, axial force or stresses induced by axial force. Then we have plus minus n my over Iyy multiplied by z plus minus by n mz over Izz multiplied by y. Now, this is where the analysis comes in. Okay, I repeat, this is where the analysis comes in. So if you look at how to identify the maximum stress, we know that down here we need to find the location of Z max, and over here we have to identify the location of Y max. Am I right? So the maximum they are, likelihood you will have, or very sure that you will have the maximum magnitude. Okay, so there's only 2 points. One is at point A, the other one is at where? At point B. Yes or no? There's only 2 points that are possible, right? So if you look at point A, right? If you look at point A, right? We have moment about Y, right? Is it going to induce tensile or compression at point A? Tensile, yes or no? If you look at moment about Z, right? If you look at moment about Z at point A, you will induce what? Tensile, okay? Right? So now, if you look at point B, My will generate what? Compression. And if you look at point B, Mz will generate what? Tensile. Can you see that now? Okay. So let's look at stress X at point A. Okay. Let's look at stress X at point A. So we calculated last week, right? So we are focusing on brass. So you see this number over here, right? You have what? 0.707 times 10 to the power 6 positive, because the axial load is inducing what? Tensile stress, okay? So 0.707 times 10 to the power 6, okay? Then you look at My. Okay, so My is going to generate tensile, so this is plus. Our reference material was brass, so this is 1. And then we calculate